What is the main problem that the proposed method aims to address in large language model training?
The main problem that the proposed method aims to address in large language model training is the necessity of the cosine learning rate schedule. The method introduces a constant learning rate followed by a cooldown phase as an alternative to the cosine schedule. The goal is to question the necessity of the cosine schedule, which requires matching the training duration to the cosine length for optimal performance. This approach aims to provide a more flexible and efficient training method that does not require determining the training length in advance. By using the constant learning rate with a cooldown, the method allows for continual learning, easier experimentation with different data mixtures, and avoids the need to retrain models from scratch multiple times. The proposed method aims to simplify the training process, reduce computational costs, and provide comparable or better performance than the cosine schedule for large language model training.
How does the proposed alternative of performing a cooldown after a constant learning rate compare to the cosine learning rate schedule? Illustrate the differences step by step.
The proposed alternative of performing a cooldown after a constant learning rate is compared to the cosine learning rate schedule in several key aspects. 1. Performance matching. The constant learning rate with cooldown schedule matches the performance of the cosine schedule, even for different training durations. This is demonstrated empirically in the experiments where the cooldown schedule shows an almost perfect match with the best cosine schedule in terms of performance. 2. Flexibility. The constant learning rate with cooldown schedule offers significant convenience by not requiring the number of training steps to be specified in advance. This allows for more flexibility during training, as the cooldown can be initiated at any time to observe model behavior and decide whether to stop. 3. Optimal loss. The constant learning rate with a short cooldown achieves the same final loss as a well-tuned cosine schedule. It is shown that the cooldown length can be less than 20% of the total training steps for long training runs to match the cosine schedule. 4. Savings in computational resources. The alternative of using a constant learning rate with a cooldown phase significantly reduces the computational resources required for scaling experiments. It enables scaling laws to be conducted for only a fraction of the previous cost, saving both time and flops. 5. Experimental comparison. Experimental results show that the cooldown learning rate schedule scales reliably, similar to cosine and stochastic weight averaging, to achieve optimal losses. The performance of the models trained with the cooldown schedule aligns closely with those trained using the cosine schedule. In conclusion, the constant learning rate with a cooldown phase offers a practical and efficient alternative to the cosine learning rate schedule for training large language models. It provides comparable performance, increased flexibility, and substantial savings in computational resources, making it a viable option for researchers and practitioners in the field of large language model training.
What are the theoretical benefits of using the constant learning rate with cooldown approach over the cosine schedule in terms of flexibility and performance?
The theoretical benefits of using the constant learning rate with cooldown approach over the cosine schedule in terms of flexibility and performance are significant. Firstly, the constant learning rate with cooldown schedule does not require the number of training steps to be specified in advance, providing more flexibility during training. This allows for the cooldown phase to be initiated at any time to observe model behavior and make decisions, enabling continual learning without the need to restart training from scratch. Additionally, the cooldown phase allows for changes in the data mixture during training, offering a form of fine-tuning that can enhance model performance. In terms of performance, the constant learning rate with cooldown approach has been shown to provide similar or even better performance compared to the optimally tuned cosine schedule. Experimental results demonstrate that the cooldown schedule can achieve optimal losses with reliable scaling behavior, outperforming the cosine schedule for sufficiently long cooldown periods. Furthermore, the constant learning rate with cooldown approach offers a more cost-effective alternative to the cosine schedule for scaling law experiments. By reducing the number of necessary training runs by one order of magnitude, it enables significant savings in computational resources and time, while still achieving optimal model performance. Overall, the constant learning rate with cooldown approach offers enhanced flexibility in training, allowing for continual learning and data mixture adjustments, while also delivering comparable or superior performance to the cosine schedule in terms of model quality and scaling behavior.
How is the performance of the constant learning rate with cooldown method validated or tested in the experiments?
The performance of the constant learning rate with cooldown method is validated or tested in the experiments by training a range of model sizes across different token scales on the same dataset. The models are trained using the constant learning rate with cooldown schedule and compared to the traditional cosine schedule and weight averaging. The validation loss envelopes are plotted as a function of training flops, and each obtained model's performance is compared with cosine and its alternatives. The results show that the constant learning rate with cooldown schedule scales reliably and achieves optimal losses similar to cosine and weight averaging. The experiments demonstrate that the model's performance aligns almost perfectly on the diagonal, indicating that both cosine and cooldown reach the same loss after the same amount of tokens. Additionally, the experiments report significant compute savings by utilizing the constant learning rate with cooldown method, enabling scaling laws for a fraction of the previous cost. The detailed results and comparisons are provided in the figures and tables presented in the paper, showcasing the effectiveness and reliability of the constant learning rate with cooldown approach for training large language models.
What are the experimental results indicating about the effectiveness of stochastic weight averaging compared to the cooldown schedule and cosine schedule?
The experimental results indicate that stochastic weight averaging, SWA, provides a significant performance boost on top of a constant learning rate, but does not reach the loss values of cooldowns at intermediate steps. SWA shows a similar boost on top of a cosine schedule, suggesting that SWA, regardless of the schedule used, offers a compelling approach to achieving strong models along the data scale axis. While SWA does not match the performance of the cooldown schedule, it reduces the gap without the need for a separate decay phase. SWA improves performance along the training trajectory and provides better models during training, serving as a replacement for models trained with fewer steps if the performance gap is acceptable and one wishes to avoid cooldowns. Ultimately, SWA offers a cost-effective and efficient alternative to the cooldown schedule and cosine schedule in large language model training.
What limitations are highlighted in the paper regarding the proposed method and its application in scaling law research?
The limitations highlighted in the paper regarding the proposed method and its application in scaling law research include the focus on models up to 360 M parameters and training on up to 10B tokens, acknowledging that behavior may change at modern scales. However, the approach of a constant learning rate followed by a cooldown has been successful at larger scales for released models. Additionally, the paper exclusively focuses on training or validation loss, while downstream tasks are the main metric of interest, which may behave differently and require further research. The paper also mentions that while downstream tasks often scale reliably with the loss, this remains an important question for further exploration, especially when coupled with different data mixtures during the cooldown phase, which is beyond the scope of the current work.